All right, as we move into section 5.9, this is the last section that we're covering here this year in chapter 5, we're going to get back into a little bit of the graphing of polynomial functions that we did at the very beginning of chapter 5, but we're looking at it a little bit different way here. And we're going to hit this T word again, guys, transforming functions. We are diving in yet again, now this is the third time this year, to the concept of learning something about parent graphs or parent functions and then doing transformations on this. So we're going to begin with the most basic cubic function that we can draw, everybody. F of x is equal to x cubed. And this is basically the way Algebra 2 works, guys. Every chapter we get into, we learn about a new kind of function, and we learn how to do two things with it. We learn how to graph it, and then we learn how to solve equations that involve that particular style of expression. Now, we've been doing equation solving since early on, really in 5.2 and 5.3, and moving on since then, but we're going to get back to graphing. Now, the hope would be that you guys know what the graph of y equals x cubed looks like, and that we can kind of use that to do all of the graphing we have to do in the future. But it's entirely possible right now you guys don't know what that looks like. I don't actually know that we've covered it in our notes. So one of the things that I want to make sure everybody understands by the time they get out of Algebra 2, this is actually something you should have known coming out of Algebra 1, but sometimes it gets lost in the shuffle. You can graph any function. I don't care what kind it is. Linear, quadratic, cubic, exponential, logarithmic, trigonometric, rational, radical, whatever. You can graph any kind of function with this simple little method right over here. You can make yourself a table of x values and then figure out what you get for y when you put those numbers right here in for x. Now, this isn't always the most efficient method, but it always works. And in fact, this is how your calculator graphs. It just takes a whole bunch of x values, plugs them in, gets y values, and then connects the dots. So here's what we're going to do. I'm going to put in 5 numbers in the x column right here. I'm going to put in, let's go least to greatest. I'm going to put a -2, a -1, a 0, a 1, and a 2. And let's see what happens. And I'm actually going to start right here, guys, because 0 is the easiest number to deal with. Let's put those x values in right here and see what we get for y. 0 cubed, hard math right here, is 0. So I now know that this graph passes through the origin. And you want to ask yourself at this point, does that give me enough information to know what this graph looks like? And the answer to that is most definitely no. So we need to keep going, and we need to graph a little bit further now. All right, so now that we know that 0, 0 is on there, let's put in a 1. 1 cubed, 1 to the 3rd power, is 1. So we get the point 1, 1. That wasn't too bad. And when we plug a 2 in there, 2 to the 3rd power, 2 times 2 times 2 is 8. Now, right about now, I run into a little trouble, because if I go to graph 2, 8, I go right 2 and up 8 units, and my graph only goes up to about 6 2/3, but that's close enough to 8, good enough. Now, what this kind of looks like, if you take a look at those 3 dots, I'm hoping you can tell me this is a non-linear function. If it were linear, it would just keep going through those same 2 dots right there, but obviously it misses this point. So no, this is a non-linear function, and it looks a lot like a parabola on the right-hand side. Now, I shouldn't use that word, because what we're dealing with is not parabolic for reasons that are kind of technical and nerdy, and you guys probably don't care about. But let's just say it curves upward like a parabola does. The interesting thing, though, with cubic functions is what happens when you start putting in negative numbers. So when we take -1 to the 3rd power, -1 times -1 times -1 is -1. We end up with a negative result right there. And we move into the 3rd quadrant. And then lastly, when I put in a -2, -2 times -2 times -2, that's a -8, and that gets us a point that's down here somewhere. So, with those 5 dots, that should give us a pretty decent representation of what this thing actually looks like. Now, real quick, before we connect the dots, there's a right way and a wrong way to do this, and it's not really important. I'm not going to take off for it. But those of you who keep taking higher levels of math, if you get to calculus at some point, this will actually become important. What is tempting to do right now is to notice that these 3 points right here, don't write this down, guys, that these 3 points are collinear, and to just connect them with a line here and then curve this one up like that. And this is the way that a lot of people want to draw this graph. And it is ever so slightly wrong. What you shouldn't do is connect those 3 dots with that straight line. What you want to do instead, guys, is coming out of the origin, this graph is actually running horizontally like that, ever so slightly, and then it curves up quickly and looks something like that. Okay, so it does this, and it comes horizontally out of the origin to the left, and then curves down pretty quickly right that. I know that seems really, really, really minor here, guys, but let me see if I can find a way, if I can find a way to show you guys that I'm not just making stuff up right here. Let me go to Desmos right here. Let me go ahead and type in the function we were just talking about. I know you guys tend to believe a calculator more than you believe me, which hurts a little bit, but okay. Y equals x cubed, and there it is. And I think you can see then as I zoom in really tight on the origin, it's actually horizontal, just for a short period of time right there, passing through the origin. As opposed to, let me show you something else, and I know you guys don't really know what this means yet, but if I did y equals, this is something in trigonometry called the tangent of x, that one does what I did the first time. That actually runs through the origin at a 45-degree angle with a slope of +1. So not a big deal right now, but I want you guys drawing this the way that that green curve works right here, rather than the way that the purple curve worked. So again, I won't take off for it, but there you go. This, everybody, this is your parent function of y is equal to x cubed. And every other function we're going to draw in this section of notes now is going to be based off of this parent graph. So this table method right over here, I want to be clear, it always works, you guys, and it's a great thing to do if you get stuck and you're not sure if you're graphing something right or not, but it's a little bit, what do I want to say, childish maybe? That's condescending there, but you know, this is the way you learned how to graph lines in 7th grade, just by making a table. It always works, but you guys are smart people. You're going to notice patterns here overall, and I want you guys to utilize those patterns as we move on. So let's take a look at a second problem. We're going to graph each polynomial function now as a transformation of the parent graph that we just drew. So y is equal to x cubed plus 3 is the next one we're going to draw. And what I want you to notice is, don't do this in your notes, but if I just cut it off right there, y equals x cubed, that's exactly the graph that we just came up with. The only thing different now is that there's a plus 3 at the end of the function. And as I said, we learned this twice already earlier this year. Once in Chapter 2 when we were drawing absolute value V graphs, and then again in Chapter 4 when we were drawing parabolas in vertex form. My question for you guys is, what does a plus 3 at the end of any function do for it? I'm going to let you think about that for a second. The answer to that, everybody, a plus 3 at the end of your function is going to move your graph up 3 units. Now, that's the answer. All right, we'll graph it right now and go. We were going to use the table in a minute just to verify that idea, but here we go. The normal parent graph, let's go back to this one right here. The first point we plotted was the origin, 0, 0. Now, that point, there we go, that point 0, 0 has been moved up 3 units. So instead of starting my graph right here, I'm actually going to move that point up to the point 0, 3. And that's where this graph actually begins. And then from there, guys, that's the only change now that's happening in that graph. So that shape that I drew in the previous graph, okay, I started my last graph at 0, 0, and I drew a curve that did this, and then a curve that did this. I'm going to draw that exact same curve again now. But instead of starting at 0, 0, I start at this point right here, which is 0, 3. And I think it's going to look something like this. And I think it's going to look something like this. Now, if the directions just say to graph it, that's probably good enough. If your directions specifically tell you to include a table with 3 values or 5 values or something like that, you might need to do this. Furthermore, this is just going to verify, I hope, that we got this right. Let's put that 0 in first, and let's do the math, everybody. 0 cubed is 0, and when we add 3 to that, we get 3. Sure enough, That's the point I was expecting. What happens when I put in a 1 right here, guys? 1 cubed is 1. 1 plus 3 is 4. And if I were to plot the point 1, 4, that gets me right there. Yeah, that looks like I've drawn this thing correctly. And if I were to go left and put in negative 1 cubed is negative 1. Add 3 to that, and you're going to get a positive 2. So negative 1, positive 2 is right there. Yeah, those 3 points kind of verify that we graphed this thing correctly. So if the directions just say graph, you can do what I did here just a second ago and be done very, very quickly with these problems. If the directions are more specific and they tell you you have to come up with a table of values, then obviously you need to do that. So we just need to read our directions carefully, whether it's on our 5-9 homework or whether it's on a test coming up soon. All right, let's do another one right here. Ooh, all right. So in that previous problem, there was a plus 3 at the end of the function, no parentheses, and that moved us up 3 units. In example B, there's a plus 5, and that happens inside the parentheses. That's different, guys, than a plus 5 happening out here at the end of it. So here's the question now, and again, it's the 3rd time this year we're talking about it, although we didn't do great with this the first 2 times around. What impact does it have on a graph to add 5 to x inside the parentheses? Well, the previous problem was a vertical shift. We went up 3 units, and if this had been a minus 3, we would have gone down 3 units right there. This graph, I'm hoping you can tell me, is a horizontal shift. This one is moving either left or right. And the tricky thing about horizontal shifts, at least to me, they're backwards from what would probably be considered intuitive. A plus 5 here actually means that we are moving left 5 units. So let's think again about our starting point, guys. We usually start our graph from the origin, 0, 0, but I'm now going to not put that dot right there. I'm going to move it 5 units to the left. Ooh, that was weird. I'm going to move it here 1, 2, 3, 4, 5, right over there. And now I think I'll go ahead and, wait a minute, let me get rid of that. Okay, and color that dot in. And I think that this thing is beginning at the ordered pair negative 5, 0. Let's check that real quick. Negative 5 goes in for x, plus 5 makes 0, and 0 cubed is 0. That's exactly what we wanted right there. So locating the starting point is really the hard part. After that, guys, that's the only transformation that's being done here. So I'm going to draw the exact same curve now for the 3rd time. A curve that shoots to the right and goes up very quickly like this, and then from that point it goes left and goes down very quickly like that. And if the directions are just telling me to graph it, okay, I'm pretty much done. If they want a table, this isn't a bad way to verify your answer, but here we go. We already did the negative 5, guys. We put the negative 5 in here, got 0, and cubed it to get 0, so we know that that one is right. Let's see, to the, it doesn't matter what order, to the right of that, I'm going to put a negative 4 here. Let's see what happens there. Negative 4 plus 5 is 1. 1 cubed is 1. And negative 4, 1 is this point right here. That looks pretty good. And how about negative 6? Negative 6 plus 5 is negative 1. And negative 1 cubed is negative 1. 6, negative 1 gets us right there. Okay, this is looking pretty good. If you wanted to go further, you could. But I think with those 3 points matching up, we're in pretty good shape. All right, so hopefully you guys are getting the idea right here that once you know your parent graph, most of these graphs are going to go pretty quickly. Okay, what is happening here, guys? In example C, we're graphing y equals the opposite of x cubed. You'll notice there's no number added at the end, so this graph is not moving up or down at all. There's no number added or subtracted with the x in parentheses before the cube, so there's no horizontal shift right here. All that we have now is this negative sign out in front. And what does that do? Taking any function and putting a negative in front of it is going to flip your graph right here. So this one is going to reflect over, this one reflects vertically, top bottom, guys, over the x-axis. So that starting point at 0, 0, which was normally right here, when you flip this graph over the x-axis like that, nothing happens, guys. That point stays right there. And I guess let me go ahead and verify this while I'm going along. I'm thinking that when I put in a 0, I still get 0. Order of operations is important here. You put in a 0 for x, you cube it first. 0 cubed is 0. Then you take the opposite of that result. Yeah, 0, 0 works out. Okay, so we've got that point. But now, don't draw this, guys, the normal parent graph would go up on the right and down on the left, but this one is flipping. It's reflecting over the x-axis. So what I believe this graph is going to do is instead of going up on the right, I think it's now going to go down on the right like this. And instead of going down on the left, it flips and goes up on the left, looking like that. So let's find out if I'm right. I'm going to put in a -1 and a +1, and let's see if we're on the right track. I'm going to do the +1 first. +1 cubed is equal to 1, and the opposite of that, -1. So we get the point 1, -1. Yeah, looks like we're doing okay. What happens when we put in -1? -1 cubed is -1, but then the opposite of -1 is +1. And -1, 1 gets me a point right there. So, okay, feel pretty good about this one right here. That negative in front of the entire function just flips the parent graph over the x-axis, top to bottom. Okay, all right, moving right along right here. Y is equal to, 3x cubed. Now again here, just like the last one, no vertical shift, nothing added at the end. No horizontal shift, nothing added inside parentheses, but our x cubed is being multiplied by 3. And again, we saw this both with absolute value v's and with quadratic u's, parabolas. What happens right here? What we're dealing with right here, guys, is what is called a vertical stretch. This graph is actually getting 3 times taller than it normally would be, and that's what's happening. That's the only change happening right here. So normally we start at the origin right here, and the height at that point is 0. When we multiply that by 3, nothing changes. We're still going to begin at the point 0, 0. And again, not a bad idea. If you want to verify that, what happens when I put in a 0? I take 0 cubed. Remember, guys, exponents happen before multiplication. It was the same thing on the last problem. 0 cubed is 0 times 3 is 0. So yeah, we've got this right. The only thing that's a little bit different right here is now when I put in a 1, let's see what happens. 1 cubed is 1 times 3 is 3. Normally the second point that I graphed was right there at the point 1, 1, but now that graph is stretching vertically by that factor of 3. So I'm going to color in that dot right there. And you can probably guess now what's going to happen when we put in -1. -1 gets cubed to make -1. Cubed is -3 as well. So this looks really similar to the first graph that I just drew. It's just that this graph is taller. It's stretched top to bottom more so than the previous parent graph was. But you'll notice that actually has very little impact, you guys, on what the shape of this graph looks like. Although really, that one almost looks more like a straight line than the original parent graph we had right here. That curve that this function takes in the middle is more pronounced right here and less pronounced now when that factor of 3 is in front. That stretches it, which makes it taller. And remember, anything taller gets the appearance of being skinnier or narrower than the parent graph was. All right, so that's how you handle something like that. Okay, F is very similar to what we just did. Apparently I skipped E. Mr. Fontana is not good with his alphabet, kids. But anyway, here you go. This graph is going to be very similar to what we just did, but now 2 little changes. The coefficient out in front is negative, and what we call that A value right there is a fraction. It's a number that's less than 1. So what's going to happen here, guys? First of all, the negative is going to flip this graph top to bottom. Okay, we did that 2 examples ago. Then that 1/2 right there is going to change the vertical scaling of this graph. And in the previous example, when we had a 3 out in front, we called that a vertical stretch because that 3 is larger than the normal coefficient, which is 1. In this case, that 1/2 is smaller than 1. That's going to give us what's called a vertical compression. This graph is actually going to be shorter than a normal graph is. And a graph that's shorter gives the appearance of being wider. But again, there's no horizontal and no vertical movement right here, so I think that my normal starting point at the origin is still going to be my starting point. But let me double check that just to make sure. When I put in a 0, we take a 0 cubed, which is 0. We multiply that by -1/2, and we still get 0. So yeah, my starting point is in the right spot. But now, here's what I think, guys. First of all, this thing is flipped. Instead of going up on the right like this one's going to go down on the right. And the 1/2 makes the graph shorter, which makes it appear wider. So I think this graph is probably going to do something like this over there on the right-hand side. Now, is there any chance? I probably didn't do that quite right, but let's see what happens when we put in +1. 1 cubed is 1, and -1/2 of 1 is -1/2. So actually, 1 -1/2, I did okay with that. However, I was looking ahead here, guys. If I put in a 2, I don't think my graph is super accurate. 2 cubed is 8. Half of 8 is 4, and then the negative makes that a -4, and I didn't do a good job hitting that point right there. So let me get rid of this little curve that I drew right here. How do I do that? I think if I hold that down, I can just delete it. There you go. All right, guys, and I think I can draw a more accurate curve now hitting those points. Ooh, I almost goofed up. You guys see what I'm doing right here? This would cost you a point. I moved that curve back over here to the left. It's bending in. You want to make sure you don't do that. All right, so basically it's going to do something like, no, I almost did it again, but all right, something close like that. And then I can kind of mirror what's happening now on the other side, and I think it's going to look like that. Let's check it. If I put in a -1, -1 cubed is -1 times -1/2 is +1/2. So -1 1/2, yeah, that's pretty close. If I put in a -2, -2 cubed is -8. -1/2 times -8 is +4, so -2/4 gets me right about there. So that graph is flipped compared to the original graph, and it's been compressed vertically. It's actually been pushed back in towards the middle here. This graph, we would say, is shorter than the parent graph, which gives it the appearance of being stretched wider or fatter than the original one was right there. All right. Hopefully, guys, all these transformations are coming back to you here. And I've got one last example to do with you, although I wrote this the old way and I forgot to fix this. So what we should be writing here is, let's do it this way. I'm going to put an x minus 3 quantity cubed and then a +2 there. So let's ignore that. And this is accomplishing the same thing. All right, that's what we're looking for. And now for the first time here, guys, we're going to throw a couple of different ideas together. So we got to think of, actually, you know what? Let's make this a little more interesting. I'm going to put a negative in front of that 2. You guys can handle it. So 3 things to think about. What does that +2 at the very end of the function do for us? That's moving us up 2 units. What does the -3 with the x in the parentheses do for us? That's a horizontal shift, and that is moving us to the right by 3 units. And what does the negative out in front do? That one is a vertical flip. Okay, so with those 3 things in mind, let's think now. Don't put this in your notes just yet, but my normal starting point is the origin, but I'm going to move that point up 2 units, 1, 2 up, and then right, 1, 2, 3 right here. The flip doesn't impact this starting point here at all. So I believe, I could be wrong, but I'll verify, I believe that my starting point here is 3, 2. But let's not just assume, everybody. It's not that hard to check this, and this is a great habit to get into. When x is 3, we should end up with a y value of 2. Let's check it. X is 3. 3 minus 3 is 0. 0 cubed is 0. The opposite of that 0 is 0. And then we add 2 at the end, and we get 2. So yeah, we got that one right. Good, good, good. And now, we already took care of the up 2 and the right 3, now the flip. A normal cubic function goes up on the right, but since this one flips, I think this time we're going to go down on the right and look a little something like that. And then a normal cubic function would go down on the left, but because of the flip, I believe this one is going to go up on the left and looks something like that. So let's verify that. I'm going to pick a number before 3 and a number after 3, and let's see what happens when we put in a 2. All right, sorry, this is messy. I wrote all over it. 2 minus 3 is going to get us -1. Cubing that -1 is -1. The opposite of that is +1, and 1 plus 2, the ordered pair 2, 3, should be on this graph. So from the origin, right 2 and up 3, yeah, I think we're doing this okay. What happens when we put in a 4? 4 minus 3 is 1. 1 cubed is 1. The opposite of 1 is -1. And -1 plus 2 is +1. So 4, 1 is going to get us this point right here. All right, guys, all 3 of those points match what we came up with. I feel pretty confident about what we did right there. So I would think the majority of your homework would probably deal with problems like this where there's multiple transformations kind of happening at the same time. And the last problem I have for you guys right here, I'm calling this one number 3, is just the opposite of everything that we've been doing so far. In all the previous, 1, 2, 3, 4, 5, 6, really 7 examples, I've given you a function and I've asked you to figure out how to graph it. Now, they're telling you what happens to the function. You've got to come up with the equation itself. So we're going to write the equation of the graph of y equals x cubed, just a normal cubic function with a vertical stretch by a factor of 5, a horizontal translation of 2 to the right, and a vertical translation of up 4. So what's going on here, guys? We're going to end up now with y equals, and at some point here, there is going to be something to the third power, because we're drawing a transformation of a cubic. Well, what's going on right here, guys? First of all, I think probably the easiest thing to deal with is this right here. Vertical translation of up 4. So what could we do in this function to make your parent graph slide up 4 units? We're going to put a +4 at the end of the entire expression. That's going back to what we talked about with the very second example that we did, that +3 at the end meant go up 3 units. Well, this +4 at the end means we're going up 4. The next one I want to focus on, I think, is this one right here, a horizontal translation, and that occurs right here inside the parentheses, where we take an x here, guys, and then we either add or subtract a number to that x or from that x. And 2 to the right, everybody. Remember, horizontal translations are kind of opposite. Moving to the right means we're actually going to subtract 2 units from that. So we have x minus 2, quantity cubed, and then a +4. And the only thing left to talk about, a vertical stretch, is what happens when you have a coefficient out in front. And a vertical stretch by a factor of 5 means that we're going to put a 5 right over there. And guys, that's it. We dealt with the vertical stretch, that was the A value out in front. The horizontal translation is called the H value inside, and then the vertical translation is the K value that gets added at the end. So that is our answer to problem number 3. Okay? All right. That's a wrap then, everybody, on our notes for section 5.9. So let's dive into that homework and see how you do. Good luck, everybody.